Welcome to another fantastic edition of Comet Algebra. This is the Algebra 2 video for Chapter 2, Section 1, Relations and Functions. Pretty much a review from Algebra 1, so I hope you remember this stuff. First, we're going to talk about the Cartesian plane, which is another term for the xy axis. Please do label x and y. The different quadrants are numbered with Roman numerals. The quadrant where x is positive and y is positive, so I'm just going to symbolize that with positive, positive in brackets like it's an ordered pair, is quadrant 1. Here, where x would be negative and y would be positive, is quadrant 2. Again, starting at the origin here, where x is negative and y is negative, puts us in quadrant 3. And here, where x is positive and y negative, puts us in quadrant 4. Next, we have some terms, definitions. A relation is any set of ordered pairs. So anything that we graph on the xy axis is a relation. Not all of them are functions, however, we'll talk about that in a moment. Domain is all of the x values, which we also call the input, the number that goes into the equation for x, and then you do the math and you figure out what the output is. The range is the y values. Now we're going to talk about these two terms a lot this year. Domain and range, you can think of it as where does the graph exist? What's its address? Where does it live? So an example of that could be just some ordered pairs. And if I happen to put these ordered pairs on a t-chart or a table, this is what it could look like. And you could be asked to state the domain and range. Well, you would state that with set notation. So I could say D for domain is the set of all x, wow, beautiful bracket there, is the x's, -1, 1, and 3, and the range is the y values, -3, 1, and 5. You also need to know what a mapping diagram is. Can be another way of expressing this relation. If we put all the x's, the domain elements, in the first circle and the range in the second, and then we draw arrows to indicate this x maps to this y, and so on. So just to show you what a mapping diagram looks like. All right, now we need to review what a function is. Functions are special relations. Not every relation is a function, so we have to learn how to distinguish that. A function is when each element in the domain maps to one and only one element in the range. Another way I've said that is each x can only have one y. But the vice versa is not true. The y's can have more than one x, and it's still a function. And we'll look at that in the mapping diagram, and we'll also look at that on a graph. In these two examples of mapping diagrams, we are asked to determine, is this a function? Now in this example 1, it may look a little goofy because each of these x's, the 1 is mapping to the 3, as are the -2 and 4. And if each x can only have one y, this is following that definition of a function. Each of these x's maps over here to only one y of 3. So we would say yes, this does represent a function. So now look at example 2. Does this one represent a function? Well, 3 maps to 0, so far so good. But here we have a problem. This -5 is mapping to the 0 and to the 4 in the range. And so it's the -5 that is breaking the rule. So here we would say no, this is not a function. Next term to review is the vertical line test. If you recall, this test, if you picture yourself drawing vertical lines anywhere on the graph, and if all of the vertical lines you can draw intersect at only one point, then we can say yes, it's a function. And this would show if we hit more than one y on a given x, that's why it shows up as that it would not be a function. So again, picture yourself drawing vertical lines all throughout this graph. This one hits it once, this one hits once, but right here at +1, we hit twice. So we would have to say, no, this one is not a function. All right, this is just a line in the second graph, and any vertical line you draw is only going to hit once. So we would say yes. This is supposed to look like a parabola that gets bigger and bigger as it goes out on both sides, and any vertical line you can draw there would only hit once. So we would say yes, that is a function. Here, this is supposed to represent a sideways, an x equals parabola, and obviously if I draw a vertical line there, it hits twice, so we would say no. And any circle that you would draw anywhere on the graph, a vertical line could hit it twice, so again, no, not a function. All right, a couple more terms here. Independent and dependent variable. Again, review from A1. An independent variable is the input, which is the domain, which are the x values. We graph the independent variables along the x-axis, just so you're connecting all these terms together. The dependent variable, again, it's the output, it is the range, we graph it along the y-axis, just so you're aware all these terms are connected. A couple more terms that this book uses is abscissa and ordinate. I believe they use these terms in this section, and I'm not sure we'll see them again. I just wanted to point out the abscissa is the x coordinate and the ordinate is the y. Next thing to look at is function notation. And we need to know how to read function notation. This first letter is not a variable. It's a name. This function's name is g. And g is going to tell you to take x and do something. Perhaps it's going to tell you to square it and add 7. Then any input, any x that comes in, you would square it, add 7, and get the output, and get the y. The other thing we need to know when we're working with these, and this is kind of to help us with our calculator, if we are given x plus y equals 12, and I asked you to graph that on your calculator, you would subtract an x from both sides and write y equals 12 minus x. And now if I asked you to change this into function notation, the f of x and the y are interchangeable. So we could call this function f, we could give it a name and call it f, and saying f is telling you to take all x's and subtract them from 12. So this helps us move in between function notation and the y equals key on our calculator. So just to sum up, f of x, or any letter here, g of x, h of x, anything written in function notation is the same thing as saying y equals. We also need to look at the terms continuous graph and discrete graph. Well, a continuous graph is sort of just what it sounds like. A line like this cruising along that keeps going forever is a continuous graph. A parabola. These are, you write them without picking up your pencil, maybe is a good way to say it. Whereas discrete graphs are just made out of dots. And a discrete graph would look something like these dots. This could represent, I don't know, maybe the price of something in your store. The price used to be up here, and then you marked it down, and you tried to get it on sale, and then you marked it down again. And the reason these aren't connected, because at no time was your item priced in between these two. It was just at this price or this price or this price. So when we would use these two graphs depends on the real life situation. Sometimes it does not make sense to connect the dots. All right, the last thing we need to look at is to be able to find the domain and range from a graph. And this is a skill we will need to use all year. So let's review it. Here we have 2 points, -3, 1, and 2, 4, and a line segment connecting them. And we are asked to find the domain and the range of this line segment. So you can think of it, where does this line segment exist? And to remind you, we are looking sideways back and forth along the x-axis when we're thinking about domain, because the domain is the set of all x's. So coming along here with your eye, where does it start existing? Well, right there. It starts existing at -3. So that's my lower boundary for the domain. And I'm looking here, this is a solid line, a solid dot, a circle filled in for the -3. So we know that it does include the -3. Therefore, I'm going to say less than or equal to. And now we're going to talk about all the x's in between here. Because this line is solid, it exists all these x's. So as I'm coming here to -2, -1, 0, it's still existing. 1, and then right here, when you hit 2, that's the upper boundary. And this is also a closed circle on 2, so I know it is included. So I would say less than or equal to 2. So we put the lower boundary here, the upper boundary here, and this is a set. It's the set of all x's such that -3 is less than or equal to x is less than or equal to 2. So now when we look at range, our eye needs to shift here to the y and start looking up and down. So your eye is traveling up the y-axis. It does not exist down here in negative land. This segment does not exist at y equals 0, but right here it starts existing at 1. So 1 is the lower boundary of the range. Again, it is a closed circle, so it's less than or equal to. Range is y values, so I use the y variable. Okay, it exists here at 1, it exists at 2, 3, but right here at 4 is the upper boundary of the range. Closed circle, so 4 is included, so I would say less than or equal to 4. And that's how we state the range when there's limits on it. All right, in this parabola, again, we're asked to find the domain and range. So for domain, we are looking back and forth here sideways along the x-axis. And this parabola continues to get larger and wider in both directions. So if you can imagine this thing getting wider and wider and wider, there is no limit. This exists over here at positive 4 million, and it'll exist this way at negative whatever. And so there's no limit on the range, on the domain. So we use a different capital letter R that stands for the real numbers. And you can just say domain is a set of all reals, or some students prefer to write it in words, the set of all real numbers. Range, however, when we shift our focus to the y-axis and we look up and down, this parabola does not exist down here in the negative. And right here at 0, we see this closed circle, or it's touching the x. It starts to exist, and of course it goes on forever in this positive direction. So the range would be the set of all y values such that y is greater than or equal to 0. All right, now you have the knowledge you need for 2.1. Have fun.